non-simple hypothesis test or testing problem, then oftentimes like the UMPs do not exist. There is a natural extension of the LRT LRT is like the likelihood ratio test. And there's a generalization which is called generalized likelihood ratio test, or just the likelihood ratio test in this case. And what you do is you look at the maximum likelihood over the entire parameter space and over the null parameter space. And you form the ratios. And so we sort of argued that this has to be very close to 1 when we're under the null, and hopefully large when we are away from the null. So an idea is to try to threshold this. So when this is large, we're going to reject. So the so there are like a couple of questions whether this is a good test, like these are theoretical questions, and the practical question is how to actually set the threshold so that let's say you have a type 1 error alpha, or like level alpha. So in general, you could try to form a test like this, where instead of this, we will look at 2 log L. And the point is that this quantity 2 log L, we can sort of drive an asymptotic distribution for it. And then you don't have to worry too much about how to set the threshold under the null if you let like if you think about asymptotic or you're okay with asymptotic like approximations. So the result is something like this. If I have a null which is let's say d minus r dimensional, so that was the setting that we had. So you have let's say omega is a subset of RD. Let's say it's an open subset of RD. It could be like the entire RD. And then you have some restrictions on the parameters like this. So the first R coordinates are 0. This is a D minus R dimensional subspace of omega. And the result is that then under the assumptions, the same assumptions that we had for the asymptotic normality of the MLEs, this 2 log L of x, which is the generalized likelihood ratio statistic, this convergence distribution to a chi-squared with r degrees of freedom under the null. And you can think of this R as the difference between the dimensions of the 2 spaces. So the full RD has dimension D, and then this has dimension D minus 1. And so the difference is, or you can think of it as the number of constraints basically you have to go from the full parameter space to the null parameter space. So this is a very interesting result, because then you don't have to worry about how to set the threshold. You just look at the quantiles of the chi-squared with r degrees of freedom, and so this result is stated for like linear hypotheses, but this essentially works for any manifold like sufficiently regular, and these are the dimensions of the tangent spaces basically. So if you think of a manifold that imposes R constraints, then if you think of the tangent space, you can like in a basis, you can look at the tangent space like that at the true parameter, and everything sort of goes through. So this is a fairly general result. But I'm doing it in this simple case. So the proof, I'm not going to repeat, it's just an application of Taylor expansion, similar argument. And the point is that we really expand on and around the theta hat n. And what happens is that the first order term goes away, because theta hat n is like unrestricted. And so you get the difference. This Mn is the sort of average log likelihood. The difference looks like a quadratic. And the end result is something like you can write this gamma n as sort of a distance. So it measures a distance in this new norm that we defined, which is based on the Fisher information, plus some OP of 1. Okay, and then at this point we sort of simplified further, assume that the null is actually a single point. So it's just theta naught. In which case this is the restricted MLE. This is just theta naught. There's no need to actually maximize anything. And so this is just the deviation of the MLE from its true parameter, and this we know is asymptotically normal. So we know this, for example, this converges to something like this. And then you can like apply the continuous mapping theorem. This function, this norm is continuous. You apply it to both sides, and you can see. So this converges to the norm of basically this new norm squared. And if you expand that norm, so these Fisher informations cancel out, and this would be like z, the norm of z squared. And the norm of z squared has chi-square distribution. So this converges to a chi-square distribution with basically d degrees of freedom, because omega naught here is 0-dimensional. And so you can think of this as the special case where this is, these are all zeros all the way to d. Theta 1 up to theta d is 0. It's just a origin. So in a more general setting, you have to worry a little bit about this, because we want an asymptotic distribution for this, but you have to sort of take the constraints into account. And I'm going to skip that. So if you're interested, you can look at chapter 17 in Keener. And there he actually does the analysis. The notation is a little bit probably hard to follow. But so what he does, just going to give you a little so say there's some sort of way. So what he's going to do there is he's going to work with a he's going to drive the null distribution of this guy under a varying alternative. So here we did it under theta naught. He's going to do it in the general case. But what he's going to do is that he's going to drive a distribution for this guy under this alternative, which means the sort of lambda n, this is the weak convergence distribution. Sometimes we write it as p theta n. This converges to a chi-squared with, let's say, r degrees of freedom, and there is a centrality parameter, which is, it's actually not delta, but something here. I don't know what I call it, some centrality parameter. So if delta is 0, then you get the null distribution we talked about, but it tells you something about the power at alternatives that are shrinking towards theta naught. So this is a rather advanced topic, and so this is like the next level of asymptotics if you want to understand hypothesis. Because if you look at any alternative as n goes to infinity, most tests sort of converge, the power converges to 1, and so all the tests are consistent. How do you know like which test is better? What you can do is you look at these alternatives that shrink towards the null, and then the differences sort of become clear there. But you require some technical machinery, because this is not a usual convergence in distribution, because the distribution of this is also changing. The underlying thing changes as a function of theta n. So you're just instead of having a single, like you're assuming that the data is generated for like usually p theta, but here you're assuming that it's generated from p theta n. So as I get more and more sample sizes, I'm going to shrink the theta towards the. So this makes the problem harder as I get more and more samples. my parameter is also closer, so the distributions are also closer. And so this requires some technical tools like contiguity, which sort of is like a nice sort of tool developed by Lucien Lecomte. And then there's like a Lecomte's third lemma that sort of tells you something about one side. So I can translate basically things under this to things under the theta naught. And so once you have those tools, you can analyze this, and there's an interesting result. And it's not much more difficult to drive the this result for k delta naught equal to 0. So if you're interested, look at Kinger's chapter 17, and he does this analysis, and you can also see what would happen to this guy, because you have to keep it on the in the omega naught, the orthogonal projection to the tangent space of this guy has to vanish, and that gives you some sort of condition to analyze. In any case, so that's chapter 17. So let's see another example, because we had some time. So suppose you have a multinomial distribution, so x1 up to xd are multinomial with parameter theta from 1 to theta t. So the parameter space itself is sort of constrained, so theta has to be a probability distribution or a probability vector, so it has to satisfy these constraints. And so xj counts how many objects out of n fall into category j, and this is the PMF. So PMF is proportional to this. So multinomial is just a generalization of the binomial distribution. If you do the MLE over omega, it's simple to drive. Hopefully people know how to do it. You could do Lagrange multiplier. So you can ignore this, enforce this condition by Lagrange multiplier argument, and take the derivatives that are equal to 0 and try to satisfy this. In the end, the MLE is just xi divided by n. Just do it as an exercise, okay? If you haven't done this, take the log of this, right? You want to maximize it, but if you try to set the derivative equal to 0, it doesn't work. But you have this constraint. So the log of this plus lambda times the summation minus 1. You set equal to 0. So now suppose I want to test whether this is coming from a uniform, which is 1 over d everywhere. I can apply or construct this generalized likelihood ratio test, and what I would get is so this is the likelihood ratio, and just to take the log, you would get this. And at this point, what I'm doing here is I'm multiplying by n, dividing by n here. Okay, so if I multiply by n, divide by n, xi divided by n is theta hat I. And so this you can think of as the KL divergence between, this is a probability vector, this is another probability vector. So interestingly, this object, which is like the generalized likelihood ratio test, measures rescaled KL divergence of this estimate from theta naught. And this is a very natural, so a lot of the times especially in multinomial cases, when the things that you drive make a lot of sense out of GLRT. And so so you reject when this is large, and you know that the KL divergence is 0 if this is equal to that. And if it's different, this measures the distance. So you're measuring the distance in this KL divergence. And so the asymptotic theory tells you that this converges to a chi-squared with d minus 1 degrees of freedom. The reason is, although the null this has 0, that dimension 0. This parameter space is constrained. So if you look at the tangent to this, it's a d-dimensional subspace. So the MLE is sort of constraints already. So you have d-1 degrees of freedom here and 0 here. So the difference is going to be the degrees of freedom, this guy. Okay. And you can see it's a non-trivial result because this is a nonlinear function. But if you're interested, you can try to prove this directly in this case because you know that these are basically, well, actually, these are not. The CLT for the multinomial would be a little bit tricky. So the xi's are, the coordinates are not independent. But yeah, so it's going to be a little bit tricky to do that. But you can write a multivariate CLT for theta hat, or for, yeah, it's just a mean. And then try to expand this around theta naught and then prove this directly, that this converges to a chi-square with d-1. Although it's just a non-trivial result. There is another version of this, which I'm not going to talk about. So for example, you can have, like in traditional like statistics, let's say you form a contingency table. Okay, anyone knows what a contingency table is? So for example, this is like, I have two things, like, I don't know. So often it's like, one is like male, female, the other like whether, so they're two variables. So you have two groups and then two other, like, there are two characteristics, like let's say binary, or it could be more. So I don't know, let's say, what is a good example? Anyone has a good example of a continuous table? Like binary continuous table. Male, female, the other one, what should we take? Sorry? Plus, minus, okay. Positive, negative, something. And then you count how many people are like male and positive, how many are female, positive, male, and negative, female, and negative. So you get 4 numbers, and you can think of this as a probability or like a count matrix, but it's also like an approximation of probability distribution. When you divide by the total number, it's just an approximation of joint distribution of these two random variables. And oftentimes what you want to test is whether these variables are independent without, and you can imagine this, you can basically, by increasing the number of categories, you can approximate any, if the variables are continuous, I can have like bins and do a binning here and another sort of binning here and just count how many, for example, fall within like 0 to like 1/4 and then 1/4 to 1/2, 1/2 to. So if it's a continuous variable, I do a binning and I get an approximation of the distribution of this guy and this guy. This would be an approximation of the joint distribution. So what you could do is, for example, test whether they're independent. To test whether they're independent, if you think about so if you think about this as it's a continuous variable, it's a multinomial variable. Okay, so it's the entire thing. You can think of it as a giant vector, which has a multinomial distribution, with n being the total number of like cases. And then if you think of these sort of probabilities, these would be like so in this case, it would be like, for example, P11, P12, P21, P22. So we can sort of reparameterize, or the theta would be like that. So theta would be like P11, P12, P21, P22. And so a null hypothesis for independence, how do I sort of test, for example, whether the joint distribution is actually whether these are independent? So I can write a null hypothesis, right? So what would be the null hypothesis here? So yeah, this sort of factorizes, which is to say that basically Pij is equal to Pi plus and P plus J. So if I sum over the first coordinates, this would give me the marginal distribution of like one of the either let's say the row, this variable. And if I sum over the rows, this would give me the marginal distribution of this variable. And so this, if this is equal to that, then this means that joint distribution is factorizing into the two marginals. So this is the null hypothesis of independence. And so you can see I can test something. This is a bit more complicated null than this, but you can see there are some constraints that I'm imposing here, right? And so you can do and so the unconstrained estimate would be similar to this. Basically, you just divide the counts that you observe in each cell by the total n. But for this, you have to solve it and like try to optimize over this constraint. And the end result would be something like the KL divergence between so your estimated joint distribution and the estimated marginals. So it's a very natural object that comes out of this. And then you can count the degrees of freedom and get an asymptotic null distribution. Okay, it's a very interesting example to do it as an exercise. I don't know if I assign it as homework problem, but this is a typical situation in classical statistics, and this gives you a very nice test for that. Okay, sounds good. There are two other things that I'm not talking about. So in addition to the generalized likelihood ratio test, there is this thing called Wald's test, and there's another one which is called Rao's test. Again, if you're interested, chapter 17 talks about these. Rao's test. So the advantage of the Wald's test is that you don't need to worry about the constraint optimization. So what it does is don't have the see if I want to talk about this. So this doesn't require this is just based on the derivatives of let's say the constraint is g of theta equals 0. It's like a nonlinear equation. And the idea is that under the null, the unconstrained MLE approximately satisfies those equations. And then you take the derivative and say equal to 0 approximately that equation. Sort of by Taylor expansion, you get a nice sort of statistic. And then Rao's test is based on the constraint sort of MLE, and asymptotically they're often very close, these two and the GLRT. But there's a nice discussion in Keener that so GLRT has some sort of like efficiency property, so it's asymptotically efficient in a sense. But like for a fixed alternative, but like things are a little more tricky. Just know that they're there if you're interested. Have a look at that chapter. So now I want to talk about any questions about GLRT. Okay, so at this point we're done with the. So any like question from the online people? Okay, so let's see if I need to switch. So at this point we're done with the things that I normally cover. So now I want to go back and see if I can talk a little bit about. So I want to go back and revisit the idea of UMP and UMP unbiased. So there are different things that we can talk about here, but this is from the book, this book. It's a very nice book on, this is Lehman and Romano, and I believe you can download it. It's like Springer if you have a UCLA account. Should be downloadable. And then What I'm going to talk about, or I just want to give you a tour of what he does in chapter 3 and 4. And it's just basically like a tour of this book and some sort of results about unbiasedness and two-sided hypothesis. So let's go to 56. Okay, so before we go there, there is some sort of a notation that he uses. So this is his notation or their notation of exponential families. So it's a little bit different. So they don't have the log partition function here, but everything is a constant there. And then there is a version where you have Q. I don't have it here. Okay, it's fine. We'll talk about that later. Okay, so this is chapter 3 about the UMPs. Most of this we have covered, but I just wanted to. So this is the result that they state about the so-called fundamental lemma of Neyman Pearson. So if you have P0 and P1, they're the probability distribution possesses densities P0 and P1 with respect to this measure. This is the Neyman Pearson lemma, and so there is an existence. So there exists a test for testing. So this is about testing like simple hypothesis, as you remember. So testing the null P0 against the alternative, which they use K for, not so there's no H0 and H1. It's like H and K, and there exists a test phi and a constant K such that a test of this form satisfies that size condition. Okay, this is what we have seen. The thing is, it has to be 1 here, 0 here, and when these sides are equal, it's just arbitrary. But the way that usually you satisfy it is you just take it to be a constant there, and then try to satisfy this. So you randomize by a constant. It doesn't have to be like that. It could be like any other sort of choice that achieves this works. So it might be non-unique. And then there's a sufficient condition. If it is satisfied 3.7 and 3.8, then it's the most powerful test, P0 against P1. This we did. This also we did. This was the necessity, which we didn't. And if you're interested, you can read it here. So like the proof. I just want to point out that there is this caveat. So if phi is the most powerful test at level alpha for testing P0 against P1, then for some K it satisfies this. And this, so it would be a likelihood ratio test, unless there exists a test of size less than alpha and with power 1. So there's this little caveat that maybe I'll talk about below, but just know that it's just almost always it's a likelihood ratio test of this form, but sometimes there could be other most powerful tests as well. So, okay, so this is, everyone remembers this one, okay. What I want to do now is talk a little bit about this geometric idea. So basically what I want to do is like talk about the cases where UMP two-sided tests exist or UMP unbiased two-sided tests exist, but I just have to tell you a little bit about this to be able to like follow what he's talking about. So this corollary says if beta denote the power of the most powerful test at level alpha for P0 against P1, then alpha has to be strictly less than beta unless P0 is equal to P1. Okay, this is a very intuitive result, and yeah, the proof you can see it's simple, but let's skip the proof. What I want to say is is it sort of intuitively clear? So the power of a test, if you're testing two different hypotheses, the power would be strictly bigger than alpha. what I want to talk about is, so that's the corollary 2.21 if you encounter it later. But what I want to talk to you a little bit about is this geometric idea. If you look at so suppose you have a test phi. If you look at the size and the power, so alpha and beta, if you remember, we can plot the size so for this test, I can try to actually there's one for one test I get one alpha and one beta, and I can plot it in the alpha beta plane. And as I vary phi, I trace these points in the alpha beta plane. Usually, like this has a threshold parameter. So it's like there's one parameter I sort of vary, and sort of you'd get something like that. Okay. So this like few paragraphs, they're trying to argue what is the geometry of this set in general. And the thing is, as I vary this alpha over all possible tests, I get a shape in this, let's say, ROC plane, if you want. What you can argue is that, let's say, 0, 0 is always there. 1, 1 is also always there, because I can get it by the test, which is identically 0 or identically 1. The next point is that it's going to be always symmetric against this point 1/2 and 1/2, because if I have a test phi, if I look at the point, like if you have a test phi, then 1 minus phi would have would realize this point. Okay, and you can imagine that this is like the reflection of a point with respect to this, if you think a little bit about this. So it's symmetric in the sense that every point here, if you reflect it against this point, it's going to end up here. And this is, if this is phi, this is going to be like, like the, I don't know what they call it, the point corresponding to phi. This would be the point corresponding to 1 minus phi. Okay, and then the next point is that this set is going to be convex because what? So the set of all possible alpha and beta would be convex. Because, sorry? Yeah, so that's these tests are like we're talking about randomized tests. So phi's are like from x to 0, 1. So a test, or in this book they're called critical functions. Keener calls them test functions. So a test function is just generally something that maps your data to 0 to 1. As I mentioned, this is interpreted as a probability of like rejecting the null. And so I can always randomize further. So if you give me phi 1 and phi 2, these are two tests, alpha, like lambda 1 or lambda phi plus 1 minus lambda phi 1 and phi 2. This test would have is going to interpolate between the 2 points. So if this is like the point corresponding to phi 1, and this is the point corresponding to phi 2, I can get everything in between by this randomization. So basically flip a coin with probability alpha, and then go with alpha this, which further sort of has some randomization. But in any case, so the point is that this region is gonna, it's good to know that this region is gonna be convex. So if you try to do ROC, sometimes you might get this inverted thing. This is like the reflection. So whatever you get here is a reflection, and this is going to be the things that are here are the most powerful tests. Okay, and these are the likelihood ratio tests, and this is like the reflection of that. So basically, these would minimize the power. So it's like when you try to maximize the power at level alpha, basically this has the maximum power, this has the minimum power anything in between has the, so there's this like symmetry, right? So if you have the most powerful test, 1 minus it has the least power. And that's the general idea. So when you try to draw these ROCs, this is what they look like. And in some cases, it would look like this. Okay, and this is where the case where you might have many most powerful tests. So at this, for example, alpha, okay, so this, anything here sort of achieves power 1. And so they're most powerful. And so that refers to that. So they may not be likelihood ratio tests. So that refers to this point here. Okay, that sometimes there exists tests with power 1 with size less than alpha, in which case those are not necessarily, at least it doesn't follow that they're necessarily likelihood ratio tests. Okay, so that's a point that I want to make. This picture allows you to reason a lot about these hypothesis testing problems. And one point, for example, is that we'll see. Okay, again, as I mentioned, this line that passes through, this corresponds to the test that's just identically equal alpha. Okay, so okay, so any question about this? Okay, so now I want to go skip this part, this one, and attempt to say something about, okay, there's duality between hypothesis and confidence intervals, which we don't talk about. Okay, so this fundamental lemma, the Neyman-Pearson lemma, if you remember, is just an application of Lagrange multiplier. Okay, Lagrange multipliers to, so what we wanted to do is to maximize expectation under, let's say, theta 1 of phi. This is the rule, subject to expectation under theta naught. So that's the problem that we try to solve. And so if you think about this, this is just a linear program in a sense. So I'm maximizing over phi, integral, let's say P1, P theta 1, or let's call it P1. That's the distribution under theta, like, let's say P1 is P theta 1, P naught is P theta naught. So this is like this times phi d mu, this is the underlying measure, and then subject to integral P naught phi less than or equal to alpha. Okay, d mu. So if you think about this, this is an infinite dimensional linear program because we're optimizing over phi. This is a linear function or functional of phi, and this is also a linear constraint. What this is doing is that we can extend the argument. So the way we did this is we say that there exists a, let's say in his notation or their notation, maximize phi instead by introducing a Lagrange multiplier. Okay, d mu minus, let's say, k integral p naught phi d mu. Okay, so the maximizer of that would satisfy, would be a maximizer of this for some k, and a maximizer of this is just p1 minus k p naught phi d mu, maximize over phi. And so the phi that maximizes this has to be 1 when this is positive, strictly bigger than 0, and has to be 0 when this is negative. And this gives you the Neyman-Pearson sort of lemma that the optimal test is a likelihood ratio test. So the one that's like positive, when this is positive, this is 1, when it's negative, this is 0. What this lemma is saying is we sort of have to justify like some of the steps because these are infinite dimensional problems, but this is basically saying I can generalize this by assuming that I have, let's say, this is like C So what they're saying is that, I mean, you could have multiple of these constraints. Okay, I could have, let's say, 2 constraints. Here is just that there are multiple constraints. So let me maybe mention this. So let's say pi, p, let's call these f's. Okay, so one constraint is that phi f1 is equal to c1 phi f, like the integral against phi f2 is equal to c2, and I want to maximize another linear function. And the idea is that the solution would look like so okay, so let me do this. So that I want to maximize, let's say p theta phi d mu subject to integral p theta 1 phi d mu less than or equal to c1 and integral theta 2 phi d mu less than or equal to c2. I can introduce 2 Lagrange multipliers. Okay, I can do say I'm gonna maximize instead over phi integral p theta phi d mu minus like k1 integral p theta 1 phi d mu plus k2 integral theta 2 phi d mu. Okay, and then this would just be integral p theta minus k1 p theta 1 minus plus k2 p theta 2 phi d mu. Okay, maximize over phi. And then you'd see that you have to, so what would be the test that maximizes this? If I did everything correctly. So the test that maximizes this would have the structure that it's 1 if p theta is bigger than k1 p theta 1 plus k2 p theta 2, 0 if p theta is less than k1 p theta 1 plus k2 p theta 2. And here you don't have to determine it. Okay, so there would be 0. Okay, so that's like a generalized form of the Neyman-Pearson lemma. So if you want to have a test that satisfies 2 constraints, sometimes they're equality, but we can easily argue that if you have a test like this, then it maximizes this guy subject to these inequality constraints. Okay, so is this sort of clear? Okay, so let me tell you why you would like to have this. So there's a lot of regularity. So whether a test like this exists or not, whether sort of you're trying to maximize, you have to worry a little bit about the fact that this is an infinite dimensional space. You're maximizing over functions. Whether I can maximize this, are there like actually tests that achieve the maximum, and so on. So that part of the test is trying to, part of that result is trying to do this. Kina also has a similar result. Okay, so that's the thing that I want to talk about, hopefully. Let's see, in 15 minutes. So let's say if you want to do a one-sided test in an exponential family, we know that we can have a UMP. And in many of those cases, we saw that, for example, there is no UMP for a test that say why not do null, the theta is bigger than 1. Sorry. Theta is in, let's say, theta 1 and theta 2. Theta not in theta 1 and theta 2. We did it for where theta 1 and theta 2 are equal. So there is no UMP test for this. This section is saying that there is actually a UMP test for the opposite. So if you have H naught is this, and H1 is the other one. So the null is everything outside this interval, and the alternative is inside. Then in the exponential family, you can find a 2-sided test. And the end of the story is that this two-sided test, the exact same 2-sided test, is going to be UMP unbiased for this one. So we have a UMP test for this, which is UMP unbiased for this, which is a little bit. Oh, sorry. the flip, basically. So you remember the symmetry that I talked about. So if you find a UMP, if there is a UMP test for this, it maximizes the power. Sorry, it maximizes the power on the alternative. So it maximizes here. Okay. And then sort of minimizes, we'll see, minimizes there. So the power, so there is a UMP test for this. So it's just, the power would look like this. So it's going to be like alpha here. So it passes through this point. There's like a maximum here. So it has the maximum power over the alternative. At these boundaries, it's going to be alpha, and it's like goes down. So it has the size alpha. And then if you flip this test, it's sort of, the effect is that it's going to have minimum power here. It's alpha here, and it goes up. And this test is not going to be UMP, but it's going to be UMP unbiased for this one. That's the whole story that I want to tell in like 10 minutes. It's sort of clear. So let's try to do this in this short amount of time. We'll see. So there is some discussion if you're interested to read about why you might want to look at a hypothesis, null hypothesis like this. I'm not going to go into this, just mathematical aspects of it we're going to focus on. There's some idea that this test, usually you do this, but this is also useful in some cases. Okay, so we first work with this, for which there is a UMP, and then show that like there is the flip of it is like UMP unbiased for this one. Okay, so let's see how we do this. So the point is, we're testing that the null hypothesis. This is the null, right? Everything outside theta 1 and theta 2. So there is you're dealing with an exponential, one parameter exponential family. I guess there is something missing here, that the parameterization is monotone. And I'm just going to assume that we are dealing with this is the natural parameter. So the parameterization is just the identity. So there is so this is the alternative. This is like the null. So there is a UMP test which does this. So rejects when t is between two values, and like accept the null if it's like outside. So this is natural. So if the sufficient statistic is outside the boundary, we reject. If it's inside, we're going to accept, because sorry, we reject if it's like this. It's the matches the structure of the intervals. So and it satisfies, it's like alpha at these boundaries, as I mentioned. So at the 2 points, theta 1 and theta 2, it satisfies these constraints. Okay, so the point is that we have a test like this that satisfies these boundary conditions. You can satisfy these boundary conditions because like you have two parameters here, and part of that lemma that we skipped, like fundamental lemma, is that you can satisfy these, but you can see why I need like to generalize the Neyman-Pearson lemma, because I want a test which is sort of which has the most power and satisfy the boundary condition. So what I'm going to strategy is find a test which is alpha at these points. That's the red one. Okay. Then show that it has most power in here, and then the power will be less than alpha also in there. So what we're going to do is show that there exists a test like this, which is most powerful. So like the constants are determined by this, and then this test minimizes the power subject to these constraints. So actually, outside this, so among all the tests that pass through these 2 points, this is the smallest power that you can have. Okay, so let me try to do this. We don't have much time. So, okay, so the first step is that we're going to work with the the sufficient statistic, you pass to the sufficient statistic, and you can show that the sufficient statistic is also going to have an exponential distribution. We didn't talk about this, but that's true. So let's say if this Q is like the eta, and let's say this is theta, the distribution of T would be, would have a density just simple, like e to the theta T, respect to like a push forward measure. So that's the density of the model that we were going to work with. So what you're going to do is build a test which is which maximizes the power, this guy, for theta prime and theta 1 and theta 2, subject to the constraints that we have here. So this is equal to alpha and this is equal to alpha. This part is arguing that yeah, so this part I'm going to skip. The existence. So the thing is, let me just give you like the overview. So the thing is, the test is going to have, suppose that we can actually satisfy these equations. This is saying that we can do. The most powerful test would be the test that rejects when p theta prime of T is bigger than like K1 P theta 1 of T plus K2 P theta 2 of T. That's the discussion that we had. And if you write these equations, it would look like this, okay? So that's the like P theta prime of T, that's P theta 2 of T, that's P theta 1 of T, okay? So we're going to reject when this happens, and then you can divide by P theta prime of T. The equations that you get is, so when you divide, so forget about the C's, these are constants, like absorb. So you get, for example, like A1 e to the Q theta 1. So I'm assuming that the Q is theta. Okay, so this, for simplicity, is just theta 1, theta 2. This is theta prime. So I get theta 1 minus theta prime T plus A2 e to the theta 2 minus theta prime T less than 1. And so one of them is negative, one of them is positive because theta is between the two. This is going to be negative, this is going to be positive. So B1 is negative, B2 is positive. And then you argue that these two, that they're two constants. We don't know the sign of them, but you argue that they have to be both positive. If they're both negative, this cannot be satisfied, or it is always satisfied. So you always reject. This obviously shouldn't be the case. If one of them is negative, one of them is positive, you can show that this region, like, it's just a one-sided interval in T, and there is a result. You can also show it yourself that then the power would be monotone. It can't sort of come back down and hit alpha. So then they conclude that these two have to be strictly positive. And what do we conclude here? Since therefore both are positive, the test satisfies. Okay, right here. .81. Oh yeah, okay. So because they're both positive, the thing is, then I can try to solve this, and the structure of this would look like an interval. So the T that satisfies this, so this function, when you plot, let's say A1 and A2 are positive, B1 is negative and B2 is negative, will be something like that. As T goes to infinity, you can see this goes to infinity. As t goes to negative, it's going to go to infinity. So the region where this is less than 1, it would be like an interval, right? So it would be like t less than like some C1 and C2. So this is the critical region would look like this. And then these constant, you just have to satisfy, like set it by this. It's very similar to the UMP argument that we had before. So the structure of the test is determined like that. It doesn't depend on the particular theta prime that we chose. Okay, so there is a test like that, and the whole point is that the interval, like these constants, it's like the threshold that we had before are like determined by these constraints. So this would be UMP because it's just this. The structure of the most powerful test does not depend on the theta prime. Okay. And the next step, we're actually out of time. So just kind of wave my hands around. But then you'd show that this minimizes if theta prime is less than theta 1 is outside, then you want to show that it minimizes. The same lemma that we had for maximizing works for minimizing, but you have to flip things. And you write down the conditions, and you argue that it's exactly the same as this. Like the structure is the same. Like these are different A's and B's, but like one is, both are positive, and this is like that. So the structure would look like this. So then when you set these two by the constraints, so the same test is minimizing things on their outside. So we have a most powerful test, which is alpha there, and minimizes things. And because I'm out of time, in the next chapter at the start, you argue that if you just flip this, because of the fact that you're minimizing here, once you flip it, you're maximizing, like among all the tests that pass through these 2 points, you're maximizing your power. And you can show that that's exactly like any test that maximizes the power outside and is alpha at the boundary is UMP unbiased. Yeah, so sorry if we had like 15 more minutes, we could do it, but just remember that this is there. It's interesting that you can, and in general, so if you read, like just the introduction, chapter 4 talks about this. In many cases, you can find these UMP unbiased tests, and the arguments are interesting if you're interested to look. Okay, thank you guys. Any questions? Okay, see you like in the final online, I guess.